Okay, so the previous part was a bit painful, but it was necessary for us to understand what support vector machines are and what are the parameters we're trying to find. So those alphas, those Lagrangian multipliers that can help us identify the support vector machine, the support vectors in the support vector machine, and determine where the discriminant is. Now, in this second part will be the more interesting one, where we're going to see why support vector machines are such a powerful classifier, because that expression we're trying to optimize and that optimization problem with those constraints that we formulated has some very interesting properties that allow us to do regularization with soft margins very easily and use this kernel trick, which allows us to do implicitly that expansion, nonlinear expansion into higher dimensions without actually having to pay the computational cost of doing the expansion. And then we're going to see how we can use this for regularization and for fine-tuning support vector machines. Okay, so let's start with the soft margins problem here. So going back to the previous lecture, we saw that to solve this problem of maximizing the margin in our classifier, we ended up having this optimization problem with these constraints. And the optimization here is to try to find the Lagrangian multipliers. There is one Lagrangian multiplier for each data point in our training set. And these Lagrangian multipliers appear because we are imposing a constraint that all the points in our training set have a margin of at least 1. That is, they are 1 unit. This is an arbitrary unit determined by the size of the vector that specifies the discriminant, but they are 1 unit away from the discriminant at least. So the end result is that all those points where this distance is trivial to respect, because they are away from the discriminant anyway, all those points get alphas of 0, because they are irrelevant. Only the points that are close to the discriminant get alphas that are above 0, and those are the support vectors, the ones that determine where the discriminant will lie. So this works if the classes are linearly separable. If you have something like this, we can identify these support vectors that have alpha values greater than 0, and these determine where the discriminant must be. But if the classes are not linearly separable, we have a problem. So we have vectors that are surrounded by neighbors that have different classes, and at some point this term here that we are subtracting has a negative terms that we are adding here that can become very important, because we have points of different classes. If we multiply -1 by 1, we get a negative value, and for those points we can get the alphas to be infinitely large, and this will give us a negative value that is infinitely large here, and this will of course become positive for the maximization, so we can start growing some alphas towards infinity, and this will make it impossible to find a solution. We cannot find the alphas that maximize this because they explode to infinity, and we don't have a solution for this optimization problem. So if we try to solve this with a non-linearly separable set of classes, then we get an error because we cannot find the alphas for this case. It's impossible to fulfill those constraints that we specified in the beginning, that all the points must be at least 1 away from the discriminant. Because if you have something like this, then some points will be on the wrong side of the discriminant, and they will have a negative sign distance, and things will not work. So one thing that we can do is, instead of forcing the margin, so this part here of the sign distance, to be at least 1, we can say that this will be at least 1 minus some slack that we can give here. So if it's possible, then it's at least 1. If it's not possible, then we can give some tolerance that we can define by this additional variable that we can create for each point in our data set. So each point in our data set has one slack variable that allows the constraint to be violated if we cannot keep the point away from the discriminant. So if this slack variable is greater than 0, then we have the point inside the margin. So if it's 0, the point is outside, it's not a problem. If it's greater than 0, then the point is penetrating the margin. And if it is greater than 1, then actually the point is on the wrong side of the discriminant. But this way, with this slack variable, we can allow for solutions even with something like this, where some points will end up on the wrong side of the discriminant. Now we want to maximize the margin again, so we put these constraints with this additional slack. We want to do the same minimization on the size on the norm of the vector that determines the discriminant plane, but we don't want these slack variables to be very large. So let's add a penalty here. So we want to minimize this plus this penalty, this C factor, multiplied by the sum of all these slack variables. So all the slack variables that are 0, this means that the point does not need to penetrate the margin, and this will not penalize anything. If we have points that start penetrating the margin, then there will be some penalization here. And the penalization will be as high, will be higher if we have larger values of C, or lower if we have lower values of C. So how reluctant we are to allow points to penetrate the margin is measured, is given by this C value here. So now we can solve the same problem. We now create the Lagrangian multiplier, but now we have an additional variable, one value for each of our data points, that is the slack variable. Since this is part of the constraint, we have one additional Lagrangian multiplier for each one of these slack variables. But to cut a long story short, if we do all the derivation here that we did in the same in the previous lecture, we end up with exactly the same set of parameters, but with a slight difference. This constraint that would tell us previously that alphas must be larger than 0 now has an additional constraint. The alphas must also be smaller or equal to C. So this is the only difference that adding this slack variable makes. When we do all the derivation, everything evens out and cuts out. So the only difference that we have now is that we have this additional constraint here. Instead of just having alpha greater than 0 that we had originally with the hard margins, we have alpha greater or equal to 0 and less or equal to C. This is the only change. So now we can do exactly the same kind of implementation. The only difference is, instead of having no upper bound for the alphas, we have an upper bound of C for the alphas. So this is one important feature of support vector machines. Allowing the margins to be softer and allowing us to solve problems like this with soft margins is only requires us to set an upper bound on the alphas. So if we do this with, say, C equals 10, this means that alphas cannot be greater than 10. We solve the problem that we had originally of alphas growing to infinity because points are violating the margins. They cannot grow to infinity, they must stop at 10. And now we have this solution for classifying this data. We have the discriminant here, separating the two classes. We have some support vectors that are exactly at the margin. So these ones have alphas smaller than 10. They are not, they don't need slack there. And we have these additional support vectors that penetrate the margins or even will stay out in the wrong side of the discriminant. And for these ones, the alpha is maxed out at 10, which is the value that we put there. So one good thing about support vector machines is that we can soften the margin here, allow for some violations of the margins with an implicit penalty on those violations, just by setting an upper bound on the alphas. And now what we can do is we can use all the support vectors. So the support vectors are still all the vectors, the examples that have alphas greater than 0, which includes the ones that are inside the margin. So these are support vectors too, and they contribute to the computation of the vector that is perpendicular to our hyperplane. Now for the other parameter there, the W0, we must use only the support vectors for which this equation is true. So we cannot use the vectors that have alpha maxed out at C, because these ones are penetrating the margin. The margin is not 1 for these ones. But we can compute this using all the vectors for which the alpha is between 0 and C. So those that have 0 are irrelevant. Those that have alpha equal to C are inside the margin, so they maxed out the penalty and have penetrated the margin. And those that have in-between values we can use to compute this parameter W0. So we can look at the actual values for the alphas in this case, and we can see that many of them are very close to 0. For example, 2 times 10 raised to minus 15, minus 12, minus 13. So all of these are effectively 0. They are away from the discriminant, they are over here or over here, and they are irrelevant for where we are placing the discriminant. Then we have some points where the alpha value is exactly 10. This is the maximum we set, the value of C. So these points where we have 10 are those points that are penetrating the margin. They are violating the constraint that we impose that the margin must be at least 1. And some of these points, for example, this one here, are actually outside, are actually in the wrong side of the discriminant. So all these points marked in red, in the red circle around them, are those that have maximized the alpha at 10, like this one, this one. And then we have these 3 points, these 3 points here. So all of these are support vectors. They all have alphas greater than 10, greater than 0, sorry. But these 3 marked in black have alphas that are greater than 0, but less than 10. For example, 2.5 here, some others here, 5.8, and so on. These are actually on the margin. They are not violating the margin constraint. They lie at the margin. The others that maximize alpha are violating the margin constraint. But only these points here matter for determining where the discriminant will be. The rest will have alphas at 0. So we can use this soft margins approach by putting an upper bound on the Lagrangian multipliers to solve the problem of non-linearly classifiable sets and still obtain a solution. However, using this is maybe good for this kind of examples where we have only a small problem with the overlap there, but it's not good if we have something that is very far from linear. So we can use soft margins here, but then we still have a linear classifier that just tries to make the best of a bad situation and doesn't get a very good classification. So here you have examples of support vectors, for example this one, that are very far away from the margin but on the wrong side, because the red side should be over here and this is on the wrong side. The same happens for these here. So all these have alphas greater than 0, but all of these that penetrate the margin have the alpha values maxed out at the value of C. It didn't go to infinity just because we set that constraint of maxing alphas at C. Then there are these ones that lie exactly at the margin, and these ones don't have the alpha maxed out. So this allows us to get a solution even when the classes are not linearly separable, but this is not a very good solution. Fortunately, support vector machines allow us to make an additional trick, which is the kernel trick. So first, this kernel is a different meaning of the word than the one we used in kernel regression. So remember that for kernel regression, a kernel was a function that was positive or zero in all its domain. It had an integral of 1 over all its domain, and it was symmetrical. That's the one we used for kernel regression. Unfortunately, the same name was used for the kernel trick, for this kernel function that has a different meaning. So in this context, a kernel function is a function of two vectors whose result is the inner product of some function of each vector. So we have a kernel function of vectors u and v that is the same as applying this function psi to u and to v, so phi of u, phi of v, and then computing the inner product of the two. So if we have this function that allows us to compute the same as the inner product of those other functions of the vector, this is the kernel function. And the usefulness of the kernel function is that it can be very much easier to compute than actually computing these transformations and then the inner product there. So let's see an example here. Suppose that the transformation we have is this one. We have the vector x with two features, x1 and x2, and we do this expansion. We take one feature to be 1, the other the square root of x1, the square root of 2 multiplied by x2, then by the product of the two, the square of x1 and the square of x2. So you see, this is similar to the kind of nonlinear transformations we did with logistic regression, where we multiply the features, we use the original features, we use the square of the features, and so on. So if this function is what we are applying to each vector, then the inner product of the result of these transformations is actually just the inner product of the original vectors plus 1 and then squared. And in general, we can have for this kind of transformation to the power of n, it's just computing the inner product, adding some constant, and then raising to the power of n. And if n is very large, this can be a very large set of features here in this expansion, and this becomes very much cheaper to compute, because the inner product of two vectors is just one single value, it's a scalar. We add a constant, we raise to the power of n, and we have the computation done. So this is very useful if we want to do some nonlinear transformation into a very high dimensional space, and then just compute the inner product of two vectors, which in support vector machine is precisely what we need. We only need to compute the inner product of the vectors. We don't need the vectors themselves. We don't need the actual examples to be transformed into higher space. All we need is the inner product of all pairs of examples. So if we have a kernel function like this one that is very cheap to compute and gives us the inner product of what this would be after some very complex transformation, we can do this transformation practically for free, because we just compute the kernel function of those vectors instead of doing the transformation explicitly. So let's see what happens here. We can replace this inner product here with the result of some kernel function. And in this case, we are implicitly expanding our data into a very high dimensional space, computing the inner products of all our examples in that high dimensional space, and then using the support vector machine as a linear classifier in that higher dimensional space. And as we saw with logistic regression, if we do that, we can increase the power of classification, because a linear classification after this nonlinear transformation is actually the same as a nonlinear classification in the original space. However, using the kernel trick with support vector machines, we can do this expansion for free practically, because we don't actually have to compute the expansion for all the examples. We just have to compute the inner product of the examples, and we use the kernel function from that. Of course, to classify the new points, now we cannot compute directly the set of coefficients, so we won't even have the set of coefficients computed. We will only have the set of Lagrangian multipliers to identify the support vectors, and then we can do the classification by using for all our support vectors the product of the Lagrangian multiplier, the class, and the inner product after the transformation, or better that using the kernel function, between each of our support vectors and the point we're trying to classify. And this will give us a value that it's either positive or negative, and that will determine in which side of the discriminant we have our point. So that will give us the classification. So when we are using the kernel trick, we can implicitly expand our data to a much higher dimensional space. It can be potentially infinite. We don't need to actually compute explicitly the discriminant. We just need to identify the support vectors and then use the support vectors to classify any new point. So if we have a new point t, we go through all the support vectors, we use the kernel function between each support vector and our point here, the one we're trying to classify, and we use the kernel function multiplied by the class and the Lagrangian multipliers of the support vectors. And if this is positive, then we put the new point in the positive class. If it's negative, we put it in the negative class. Okay, so let's see how this works. Suppose that we have a polynomial degree, a polynomial kernel with a degree d, then we just need to compute the inner product, add 1 and raise to the power of d, and we can do this easily when computing the matrix. So remember that we computed the matrix of all the inner products here multiplied by the classes of the points for all pairs of points. So we simply replace that with the matrix with all the classes and the kernel between the 2 points. So we can replace that in the computation of the matrix. We just do the inner product first and then raise to the power of d. And then to classify a point, we just loop through all the points we have in our data set, or better yet, all the points that are support vectors, because those that have an alpha of 0 are irrelevant. They will not contribute to this. And we can just determine if the result is larger or smaller than 0. So in practice, we will not implement this. We will not use the implementation using SciPy and minimize and so on. That was just to show you the different components here and what are the implications for the computational part of using this kernel trick. In practice, we're going to use this class SVC support vector classifier from scikit-learn, and then we can use different kernels or even compute our own matrix and with different parameters, and we can use that implicit transformation in order to make a nonlinear classification. So the way this works is you create an object by specifying the kernel, the C parameter for the soft margins, give the additional parameters for the kernel depending on the kernel parameters. For example, the polynomial kernel has this degree and this value here, the coefficient 0 that you add there. You can set these parameters, and then we call the fit method to fit the data to the class labels. Okay. So this the implementation that I showed here is not one to use in practice, because it's always better to use the optimized implementations. It was only to help understand what is happening here. Otherwise, if you don't understand what's happening in support vector machine, this seems to be like witchcraft, because you just put the data in and you get something in result. So if we want to do this classification, we can use a polynomial expansion, for example, of degree 2 in this case. Using c equals 1, this is the maximum value we allow for the Lagrangian multipliers, for the alphas. So since c is low, we have a very high regularization here, and we are making the margins very soft. So this frontier will tend to be less curved, and we allow more points to penetrate the margins. If we increase the degree of the polynomial expansion, in this case, we start allowing the function to become more curved. And also, if we increase the penalty, the maximum penalty for the Lagrangian multipliers, we start decreasing, shrinking the margins and forcing more points to be outside the margin. So for example, with a very high C, we have a very high penalty for points that penetrate the margin, and in this case we can even force all points to be at the margin or outside the margin. So this is the frontier that we get. Remember that this frontier is actually a linear separation, but it's a linear separation on the space that you obtain when you apply this polynomial expansion to our features. We are doing this implicitly with the kernel trick, so all we get is just the frontier in our original space. We don't have to actually compute all those expansions, but we get a nonlinear separation here. We get a curved discriminant because of this trick of implicitly expanding into higher dimensions. You can use other kernels, for example, the Gaussian RBF, radial basis function kernel, is a Gaussian kernel that depends only on the distance between the points. So this is actually an implicit transformation into an infinite number of dimensions, you can do this. We cannot do this explicit. We cannot explicitly create vectors of infinite size, but by using this Gaussian RBF kernel, we can create an implicit transformation into infinite dimensions, and this gives us much more flexibility to do these classifications, because now by adjusting this gamma parameter here, we can make the kernel wider or narrower, so we can look at points that are further away or closer to the points we are classifying. For example, with a very small gamma, we are looking at points that are further away, and with a very small c, we are allowing a lot of points to penetrate the margin. But if we increase these values, for example, higher gamma will allow us to make a lot more intricate curves here, and if we increase the value of c, for example, with a c of 1000 and a gamma of 0.5, we can actually adjust exactly to the frontier there, but different combinations will give us different results. So this is what makes support vector machines extremely powerful. The soft margins we can apply simply by limiting the maximum value of the Lagrangian multipliers. So it doesn't require any additional computations. We just place an upper bound on the Lagrangian multipliers, and we allow some points to penetrate the margin. So this is one form of regularization that we can use, which makes the discriminant be less curved, less intricate, and softens the frontier. We can also do with the kernel trick, just by using these kernel functions, since we only need the inner products of the pairs of examples in our data set, we don't need to do explicit transformations, and we can do implicit nonlinear transformations to very high dimensional spaces or even infinite dimensional spaces using these kind of radial basis functions that allow us to arbitrarily increase the power of our classifier. So basically the problem now is simply overfitting if we don't have enough data, but we can increase a lot the power of this the classifier to classify our training data. So this is really the big power of support vector machines. For example, here with a gamma of 2 and a c of 1000, we create a discriminant, and these margins are really moving around each cluster of points here. But this shape, this expression that defines the support vector machine, and solving the problem of maximization by computing those Lagrangian multipliers that determine the support vector, make this classifier extremely powerful when we combine that with the soft margins, that is placing an upper limit on the value of the Lagrangian multipliers. It's this C parameter that we can use, and to make nonlinear classifications using the kernel trick. So by using functions that are very simple to compute but give us the same result as the inner product of complex transformations of our data. Since all the support vector machine needs are those inner products, we can do implicit transformations of our data into much higher dimensions, make the classifier much more powerful, but without having to actually compute those transformations, which could be very expensive or even impossible if we are expanding to infinite number of dimensions. So this is the basic idea of support vector machines. The first part was a bit complex because of all the mathematics there, but what you really need to understand is these important aspects here, which is, first of all, we are optimizing the function to try to find the values of the Lagrangian multipliers that maximize this expression. And the expression we're trying to maximize depends only on the inner products of the pairs of examples in our data. So since all we need are the inner products, we can use this kernel trick to replace the inner products with the kernel function that gives us the result of the inner product we would obtain if we expanded the data to much higher dimensions, but without actually having to do that expansion. So because of this shape of the way we are trying to find these Lagrangian multipliers and the need only for the inner product between pairs of points, we can use these two things, the soft margins and the kernel tricks, to do regularization and increase the power of our support vector machine classifiers. So this is the important part. You're going next week. You're going to use these support vector machine classifiers and look at these results. But this is basically what you really need to understand, why these tricks work. So that means you need to understand the general function that we're trying to optimize in the support vector machine. And you should understand how we got there. Remember that the motivation was to try to maximize this margin here, so the distance between the discriminant and the points that are closer to the discriminant. And this is what we're doing in this high dimensional space after this nonlinear transformation. And when we bring everything back to the original space, we get this more complex discriminant. Okay, so that's it for now. Just give me about 5 minutes and I'll start the session in Zoom if you have any questions. So see you soon.